Hello everyone, my name is BigOCEAN and I'll be presenting on the topic of occurrence of subsurface eddy in the Terra Nova Bay and its impact on basal melting of Nansen ice shelf. In the opening remarks of the previous Climate Ambition Summit, the UN Secretary General said humanity has opened the gates of hell, warning we are heading towards a dangerous and unstable world, which means that we are now entering an era not of climate change, but of climate crisis. The meridional overturning circulation plays a crucial role in redistributing heat throughout the global ocean, thereby regulating Earth's climate. A key component of this circulation is Antarctic bottom water, which forms in Antarctica and acts as a buffer against climate change. High salinity shelf water, which is one of AABW precursors, is formed at Ross Sea, and this sea is the primary contributor of AABW. Terra Nova Bay, the place which this study focuses on, is located in the western Ross Sea and accounts for 33% of the Ross Sea high salinity shelf water production. It interacts with the nearby Nansen ice shelf, contributing the formation of ice shelf water and ultimately to the formation of Antarctic bottom water. Therefore, understanding the water mass circulation in this area and interaction with the Nansen ice shelf is essential. Recently, high-frequency variability such as mesoscale, submesoscale eddies, which have the potential to influence the Terra Nova Bay region, have been observed. However, study on this topic is still lacking compared to a lot of studies on the large-scale variabilities. According to a previous study of submesoscale cyclonic eddy which is observed via glider in January 2019, induced a welling of shelf water and tripling of surface water, as you can see from the picture on the right bottom corner. Because the cyclonic tinny lowers the surface water as much as the thickness of the Nansen shelf front, the study suggested that if such eddy approaches the Nansen shelf, it could induce the basal melting of Nansen shelf. However, during the observation period, the eddy was located far from the ice shelf, and due to spatial temporal limitations of in situ observations, the impact of the eddy could not be confirmed. Therefore, the aim of this study is to understand the role of submesoscale eddies in ice shelf cavity and ocean interaction. By using a regional sea ice ocean model that includes ocean ice shelf interaction, we simulated submerged subsurface cyclone activity and investigated its impact on the ice shelf basal melting. To begin with, let me explain about tinning. Generally, in the southern hemisphere, cyclonic eddies exhibit a clockwise rotation, inducing a whirling. When strong westerly winds blow, higher stress occurs on the flank of the eddy where the wind opposes the surface current, with the lower stress on the flank of the eddy where the wind and the current are in the same direction. So the differences between the higher and lower wind stress lead to the difference in the amount of Ekman transport. As a result, water converges toward the center. Consequently, surface water undergoes downwelling, while deep water experiences upwelling, forming a subsurface cyclonic tinny with such vertical structure. The model settings used in this study are as follows, and the figure on the right slides show the model domain and the thickness of the ice shelf. To simulate the TINI, it was necessary to consider the interaction between wind and currents. Therefore, a wind stress formula that considers the influence of currents was applied in the model instead of general wind stress formula. We conducted eddy detection using sea surface height EOF, targeting the austral summer of December and January. And as a result of the analysis, as you can see in the figure, eddy-related mode appeared in the third mode. Distinct spatial patterns were observed in each of the three cases. Among these three, I will introduce the case of 2015-2016, where the TINI was most prominently observed. The eddy appeared between January 14th to 23rd in 2016. In the vertical section based on the EOF spatial distribution, a typical cyclonicity structure, which shows unusually shallow, high salinity shelf water and anomalously deep Antarctic surface water, was found, similar to observations. The TINI appeared to approach the Nansen shelf front as eddy grows and eventually collide with it, and seemed to transfer warm surface water to the base of the Nansen shelf. To verify whether the eddy transferred heat below the ice shelf, we calculated the heat advection at the Nansen shelf front and the zonal eddy heat transport, and represented the calculated result on the vertical heat advection and zonal eddy heat transport of the time of the eddy collision. As shown in the figure, a significant increase in heat advection was observed at the point of the eddy collision, indicating that heat transport by eddy occurred across the Nansen shelf. In other words, eddy transferred heat into the ice shelf cavity as it collided the ice shelf front. To examine the response of the Nansen shelf to the heat transferred by the eddy, we averaged the melt rate of the Nansen shelf of a thickness less than 200 meters by latitude, and represented it as a Hopf diagram. In the red box, you can see that during the time when the eddy approached and collided with the front, the melt rate sharply increased even at the inner part of the ice shelf cavity. This indicates a rapid melting at the base of the Nansen shelf due to eddy heat transfer. To determine whether such a rapid melting occurs only as a result of collision, we also analyzed another case where the TINI did not collide. A cyclonic eddy occurred between January 5th to 10th in 2019, displaying a TINI structure with high salinity shelf water obeling and Antarctic surface water dipping like it occurred at the previous case. However, in this case, the TINI did not collide with the Nansen. Therefore, there was no increase in heat advection, and as a result, there was no significant change in the melt rate both before and after the occurrence of eddy. When comparing the TNB mean currents patterns during the two periods when the eddies occurred, in the case of the 1819, unlike the time when the eddy collided with the ice shelf, the mean current intensity was very strong. So it is assumed that the eddy did not collide but instead flowed along with the main current in the 1819 case. To summarize, in this study, using the numerical model that considers wind current interaction, we simulated cyclonic TD which occurs well with in situ observations. Based on the results, as eddies bump against the front of the Nansen shelf, they transfer heat across the NIS front and then induce significant basal melting of the ice shelf. Melting of the ice shelf reduces in the ice shelf stability, which may trigger fracturing and lead to calving events, resulting in the discharge of the ice sheet mass into the ocean and consequently a rise in sea level. Therefore, further consecutive observation and improved model performances are necessary and additional studies are needed. Thank you for listening to my presentation.